I'm Pat Dugas, and this screencast is operations on functions. We're going to look at sum, difference, product, and quotient of functions, combining functions together. And we're going to look at compositions of functions, taking a one function, having it serve its output serve as the input for another function. So let's begin with kind of a summary of how operations on functions work from an addition, subtraction, multiplication, and division standpoint. If we're adding two functions, let's call those functions f of x and g of x. If we're adding those functions together, f plus g of x, the combined function, is equal to f of x plus g of x. So for example, let's let f of x be 2x and g of x be negative x plus 5. In that case, f plus g of x is equal to f of x, which is 2x, plus g of x, which is negative x plus 5. When we combine those together, like terms, I get 2x plus negative x, or just x, plus 5. So that would be f plus g of x. Subtraction works a similar way. F minus g of x is equal to f of x minus g of x. For using the same example, since fx is 2x, f minus g of x is equal to 2x minus all of g of x, which is negative x plus 5. And so to combine them, I've got to distribute that negative 1 to both terms using the distributive property. And so I get 2x minus negative x, or 2x plus x, 3x minus 5. And so that's f minus g of x. Multiplication. So multiplying two functions and turning it into a bigger function, f times g of x, that's equal to the first function times the second function. So f times g of x is equal to f of x, 2x in this case, times g of x, which is negative x plus 5. And so since we're multiplying, we're going to have to distribute that 2x to both parts. 2x times negative x is negative 2x squared. And then 2x times positive 5 is positive 10x. And so that's f times g of x. And finally, division. We have to be careful with dividing, of course, because we can't divide by 0. So g of x can never take on a value of 0, or else the result is undefined. F divided by g of x, or f over g of x, would be equal to f of x divided by g of x. So again, using our example, f over g of x would be equal to f of x, 2x, divided by g of x, negative x plus 5, as long as we abide by the rule that x is not equal to 5. So let's look at some examples of each. Adding functions. So if we're given a function f of x, it's 3x squared plus 7x, and g of x, it's 2x squared minus x minus 1. We want to find f plus g of x. And again, that's how we say it. So f plus g of x is equal to f of x plus g of x by our property of addition of functions. And so we're going to substitute in the 3x squared plus 7x for f of x, and the 2x squared minus x minus 1 for g of x, and then we're going to combine like terms. We've got a 3x squared, we've got a 2x squared. We've got a 7x, and we've got a negative x, and then finally the negative 1 constant is on its own. So combining those like terms, 3x squared plus 2x squared gives us 5x squared. 7x minus x is 6x, and of course the negative 1, and that's our answer of f plus g of x in this case. Now, given that f of x is 3x squared plus 7x, and g of x is 2x squared minus x minus 1, find f minus g of x. So we're going to use the subtraction of functions property, that f of minus g of x is equal to f of x minus g of x. If f of x is 3x squared plus 7x, I'm going to take that and substitute it in for f of x, and g of x is the second expression there, and I'm going to substitute that in for g of x, and so I get this combination. Like terms, 3x squared, 2x squared, 7x and minus x, and of course the negative 1 again off by itself. We combine the like terms, we get 3x squared minus 2x squared, which is 1x squared, 7x minus negative x, which is positive x, gives us 8x. And then negative of negative 1 gives us positive 1. Be very careful with negative numbers. Now it's important to note, if I asked you what g minus f of x was, it would be a different answer because remember, addition is commutative, subtraction is not. So g minus f of x, we're not going to do it, but it would be a different answer. Multiplication of functions. So given the functions f of x equals 3x squared minus 2x plus 1 and g of x equals x minus 4, we want to find f times g of x. Now be very careful. That is a product, that closed circle. We're going to look at a composite function. You'll see that sometimes like an open circle. It looks like fog. It's really f of g. So that's not what we're looking at here. Make sure you distinguish between the two. So f times g of x, we're going to use the product property of functions. And so f times g of x is equal to f of x times g of x. Substitute in. Everywhere we see an f of x, you're going to go ahead and substitute in that term, that expression, 3x squared minus 2x plus 1. Everywhere you see a g of x, you're going to put in an x minus 4. And as you might expect, we're going to use the distributive property next. We're going to distribute the 3x squared to the x and the negative 4. We're going to distribute the negative 2x to the two terms. We're going to distribute it the 1x to the two terms. Okay, so a lot of distribution there because we have a trinomial times a binomial. So distributing gives us 3x to the third minus 12x squared minus 2x squared plus 8x plus x minus 4. We're going to look for like terms and combine the like terms, which gives us 3x to the third minus 14x squared plus 9x minus 4. And that is f times g of x, given that f of x is this first function and g of x is this second function. Now we're going to look at division of functions. Now again, we have to be careful with division. Division by 0 is not allowed. So we've got to keep that in mind as we're doing the division of functions. F of x is 3x squared minus 2x plus 1. Again, g of x is x minus 4. We're asked to find f over g, or f divided by g of x. So f over g of x is going to be equal to f of x over g of x because of our division property of functions. Substituting in for f of x and then substituting in for g of x yields this quotient, with the caveat that x is not equal to 4. We're going to move on to a topic that causes a lot of confusion, and I'm hoping to help alleviate some of that. So we're talking about a composition of function. When we compose something, we are putting it together. Okay, so let's suppose we have two functions, f and g, and they are functions such that the range of g, the output of g, is a subset of the domain of f. In other words, all the outputs of g can go into f. So the composite function or composition function f of g, it looks like the word fog, but it's actually f of g, can be described by f of g of x equals f of g of x. Now, I think a picture helps here. So it's kind of like, I like to look at it like an assembly line, a function assembly line. So let's take an x. X goes in to g of x. So x is the input for g of x. And then g of x evaluates that. So it's like an assembly line worker. G of x does something to x. That turns the x input into some kind of output. That output of g of x becomes the input into f of g of x. Okay, and then the result of that is our actual answer. Okay, so f of g of x means taking the input of x, putting it into g of x, evaluating g of x, and then putting the g of x into input of f of g of x. And then our answer is what comes off the assembly line, if you will. Let's look at an example of compositions of functions. So we're asked to find f of g of x and g of f of x for f of x equals 3x squared minus x plus 4, and g of x equals 2x minus 1. Okay, we'll focus on this first part and take care of that first. F of g of x. Well, f of g of x means f evaluating g of x as its input. It's a composition of functions with g of x as the input. So what we're going to do is, working from the inner to the outer, g of x becomes the input. So g of x we know is 2x minus 1. We're going to put that as the input to f of x. So now f of g of x becomes f of 2x minus 1 because that's f of g of x. So now 2x minus 1 is the input that goes into f of x. So everywhere we see an x in f of x, we are going to substitute 2x minus 1. So it becomes 3 times 2x minus 1 squared minus 2x minus 1 plus 4. Each of these terms corresponds to the original f of x. Because it's not f of x now, it's f of g of x. And g of x is the input. We've got to go ahead and distribute out the 2x minus 1 quantity squared. And we've got to just bring down these other parts. So one more step after this, two more steps really, but quite a bit of simplification here. When you combine them all together, you get 12x squared minus 14x plus 8. That's f of g of x. Now, if we flip it around, then it becomes g of f of x. G of f of x is the same thing as having f of x be the input into g. So we're starting with the f of x and working our way out. So what we're going to do now is put f of x into g of x. So 3x squared minus x plus 4 now becomes the input into g of x. Now we're going to evaluate g of f of x. So everywhere in g of x we have an x. That x is no longer the input. It's now f of x, which is 3x squared minus x plus 4. So we now have 2, instead of 2 times x minus 1, we have 2 times f of x minus 1. And that's where these terms here come from. 2 times quantity, 3x squared minus x plus 4 minus 1. And now it's a matter of distributing that 2 and combining our like terms to get our answer. Again, so we've looked at operations on functions, both the operations of addition, subtraction, multiplication, and division, and the more complex operation of composite functions.